Alrighty.
That's a cool class, though. It was pretty cool, yeah.
What class is that?
ESE 543, 547, the controls classes.
Oh yeah, I'm not as familiar with the electrical, right?
Yeah.
Yeah, I'm not as familiar with those.
He does an optimal control algorithm that's based off the Bellman-Jacobi equation, and that's like an underlying equation for deep reinforcement learning too. I thought it was interesting that the same equation, has such a broad use.
Yeah. Yeah, absolutely. All right. For the last hour or so, honestly, it may not even take me a full hour to talk about this one. This one is a bit easier to digest than some of that last material was. We're going to talk about speed up. So really, the reason why I'm introducing both this topic and the last topic is we're getting more into the parallel phase of things. So it's important to know how to talk about our parallel programs in terms of performance. I'm going to introduce some terminology, some of which maybe you've heard before in other classes if you have experience with parallel programming. Oh, whoops, that slide is old. Sorry, that shouldn't have been on there. I should have taken that one out. My bad. Let's talk about speed up. There's lots of different ways that we can talk about speed up. The classic one is this one up here. So take your program, run it on one core, and measure how long that takes. That's T sub 1. And then take your program and run it on P nodes, or P cores, or however you want to think about it. Measure how long that takes. It should be faster, right? I would hope if it's parallel, it's going to be faster in time. That's why we've got this one on the denominator side, because then that gives us a number that we call speed up. So if it runs in half the time, right, then we would expect a speed up of 2. We would say that's a speed up of 2 for that parallel program. We can also measure it not via time, but by throughput. So like how much work is getting done, how much actual data is being processed and output from our program, which may be useful. This one example of throughput could be flops. How many floating point instructions am I able to execute over a certain period of time, right? So that's just one example of throughput, not the only example of throughput, but a nice convenient one for us to talk about. It's the same general idea, except since we're talking about throughput instead of wall clock time, we inverse the relationship. We put the parallel one on top because we expect the throughput to be the bigger number for a parallel program. I expect a parallel program to be able to cram through more data in the same period of time than if I was only running it on a single processor, a single core. So we can define speed up that way as well. How much data am I able to cram through my parallel program as opposed to if it was running on one sequential core. And so these are kind of the classic definitions of speed up. This is a nice thing to pay attention to on future homework assignments. I absolutely would love it if you would tell me what the speed up is. It depends on which questions you answer, of course. It may not be relevant for every single question because you get to pick and choose, but for some of them, absolutely would be 100% relevant to talk about the speed up of the program, especially if you're running it across multiple cores, right? So that we can actually view the speed up over different core amounts. Oh yeah, I already kind of talked about some of this stuff. So yeah, what does it mean for a unit of work to be throughput? Flops is one potential thing that we can use. We have to be a little bit careful though. Does the parallel algorithm use the same number of operations as the sequential algorithm? We actually talked about this a little bit earlier today. Sometimes the very act of parallelism requires us to do more work because we have to take some time to divvy up the program ahead of time. So the program is actually doing more work than it would be if it was doing things sequentially, in which case it's not necessarily appropriate. We're going to get misleading figures. There's going to be more instructions in the parallel program, but is that really more work? Because we're getting the same amount of stuff done. So on paper, it might look like I'm cramming through more flops, but if some of those flops just straight up don't exist in my sequential program, it's kind of misleading. I'm kind of inflating those values. So we have to be a little bit careful about how we apply these metrics. I would say the time one is almost always relevant, right? Time, people always care about time, especially computer scientists. We care about time a lot, care about efficiency a lot. So using the time version of Speedup is almost always appropriate. Throughput is a little bit trickier to use, but still extremely valuable, especially when it comes to one of those cases I mentioned earlier with like a pipeline execution. I think we're actually going to see a slide in a little bit that shows an example of pipelined execution where the whole goal of one of the main benefits of pipelining is you get really good throughput on those pipelines. Those are the cases where it's really going to be kind of convenient. The nice thing is that there is kind of a relationship between the two where you can see that the ratio, sometimes using a ratio is enough. We don't actually need to compute the actual speed up. We can just compare the throughputs directly. Let's take a look at a more specific example using pipelining. Where should I measure throughput? Where should I measure throughput on this example? Should I wait until the whole pipeline is filled up? So you can see that it takes a while for the pipeline to get full, because it takes a while for that data to propagate through and hit every single stage of the pipeline. And then we have the same thing on the tail end where the first section of the pipeline is going to be empty while the back section of the pipeline are still running. So should we just kind of ignore those and focus only on the case where the pipeline is completely full? Or should we focus on the entire picture from start to finish? And you can see that we can actually get different numbers, different speed ups from the same execution just by slicing it up in different ways. If we focus on the middle section, you can see we get 18 units of work done over 6 units of time, which appears to be a speed up of roughly 3, right? And that makes sense. I've got 3 stages, I'm sorry, not 3 stages, I have 8 stages in this pipeline, but you can see that at its capacity, I've got 3 units of work going through at the same amount of time. So that seems like a reasonable number. For a sequential execution, though, I would expect only 6 units of work over 6 periods, 1 piece of work for each unit of time. We can see that clearly just by focusing on one bar, 1, 2, 3, 4, 5, 6 over 6. So computing the speed up based on throughput in that example gives us a speed up of 3, but if we look at it from the case of, if we look at it over time, instead of throughput, using these measurements here, we can see that we end up with 24 units over, 24 units over a given period of time versus 10 units for the third. Why is it 10? Oh wait, hang on a second. I'm sorry. This is the, my bad. This is the sequential up here. 24 units of time to crunch all of these. Imagine them all stretched out in a straight line. I got my numerator and denominator flipped in my head because it's the end of the day. The sequential would be 24 because they would all be stretched out in a big single straight line compared to if we look at the time pipeline, it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for a time speedup of 2.4, meaning that the throughput speedup, if we're computing based off of just this middle section, is inflated. Do we actually get that level of speedup? Yes, but only when the pipeline is full. Only when the pipeline is actually filled up. We don't get that true level of speed up when we take in the spin up and the wind down time of our pipeline into account. So we can crunch those numbers again, and if we crunch those numbers taking the beginning and the end into account as well, not just when the pipeline is full, you'll notice that, okay, we get 24 units of work over 10 units of time. That's 2.4. Well, hey, that more closely matches our expected speed up based off of time. The throughput speed up is going to converge to the time-based speed up. The reason why I give you this example is because, like many statistics, depending on how you slice them and dice them, right, you can convince anybody of anything if you come up with the right stats, right? That's kind of a famous quote from stats class. So you can make the numbers paint any story you want if you crunch them in particular ways. And so that kind of leads us, well, yeah, I have a slide that talks about that. I guess we're not quite there yet. Another metric that we talk about is efficiency. So if I have 1,000 cores, but only half of them are actually being used, well, I'm wasting the other half. They're just sitting there doing nothing. So how efficient actually is this program? How much parallelism are we expecting to get back out based on the number of cores versus how much speed up we actually get back out when we run the program? So if I have P cores, I really expect to get speed up relative to that value of P. But what we're going to do is we're going to take the actual execution time, so injecting that P as part of our speed up computation, and assuming that the speed up is going to be, best case equal to P, we're never going to get speed up that is greater than the number of cores. If I run something on 8 cores, would I ever expect it to run 10 times as fast or 100 times as fast? Well, there's only 8 cores, so I would at most expect it to run 8 times as fast, right? If it's truly explicitly parallel. And that's in the absolute best case. Now, that being said, there is something called superlinear speedup, which actually would say that given 8 cores, maybe I would see a speedup of more than 8. Maybe I would see a speedup of 10 or 12. That actually can happen in certain conditions. The most important condition there being, consider a very large problem. Running, that large problem sequentially is going to get me some big time. When I parallelize that large problem, what do? We just talked about it. We decompose that problem into smaller chunks. So think about the effects of that. If those chunks are now small enough to fit into memory and allow me to avoid making more trips to disk, that actually is going to get me even more speed up than just from the parallelization alone. Not because of the bigger number of cores, but because of fewer trips to, or even if they take that a step farther, what if they are small enough that now they all fit into cache even, not just memory, right? So now I'm saving time by making fewer trips to memory, fewer trips to disk, and I'm getting the speed up from the cores plus the speed up from cache. Now, that's a specific situation. That superlinear speedup only applies basically in that situation I described, where the problem has been decomposed such that it now fits into cache. And so I get the extra benefits of that as well. For most problems, that's not going to apply. So we don't expect the speedup to be any bigger than P in the vast majority of cases. The limit of our speedup is going to be bounded by the number of cores that we're using to run that program in parallel, which means that our efficiency is going to be some value less than 1. So the way to interpret that value, if the efficiency is 1, that means we're getting the best possible speedup that we could possibly hope for, right? For that to be a speedup of 1, that would mean that this has to be exactly T1 divided by P. This would have to be the exact inverse of that, because then when you multiply it together, you would get 1 back out. But if that speedup is not quite as good, so if I expect it to be, if I'm using 8 cores, I would expect TP to be 1/8 of T1 to get me the best possible result, right? But what if it's only 1/6? That could happen. It could certainly happen. That means that my efficiency is going to be less than 1. It might be 0.8 or 0.7, meaning that, okay, yeah, I did get some speed up, but I didn't reach my maximum potential. I only reached 80% of the potential that I could have gotten if I was able to effectively parallelize that program and get that pure maximum speed up that I'm always, of course, hoping that I'm going to get. But in practice, it's kind of hard to achieve for lots of different reasons. So what is our baseline? This is another important thing to think about. When I say I'm running it sequentially, what exactly am I running sequentially? Am I taking the parallel program and just running it on a single core? Does that seem like a fair comparison? I would argue no, that doesn't seem like a fair comparison. Am I taking the same sequential algorithm that is in my parallel program? So taking all the parallel stuff out of the parallel program, making it sequential that way. So starting with my parallel program, remove all the parallel stuff to make it truly sequential, and then running that on one processor. Better, right? Because now all that parallel stuff is gone that I don't really need to worry about on a single core anyway. Basically, we're extracting all of the overhead for communication and stuff that might be present in a parallel program. Better, but still I would argue not necessarily a fair comparison. The best comparison that we need to make is an optimized sequential program. So write the program without any parallelism in mind. How would you solve this purely sequential if I'm not writing with any parallelism in mind? There might actually be techniques, optimization techniques, that we could use on a sequential program that would be more difficult or not possible to use in our parallel execution based on how we decompose the problem, for example. So this is getting closer to our, this is getting to a more accurate representation of what our baseline sequential time is. And then there was, for a period of time, a group of people that suggested, hey, we should actually try to standardize the machines. And I think historically that may have been something that was not totally unrealistic, but in today's age, there are so many differences between machines. Getting people to agree on what a standard machine is would be next to impossible. So this idea has been relatively abandoned, right? 3 is certainly, I think, the more honest one of the two. Not to say that comparing things using the first couple of options is completely useless if you're trying to understand the effects that the parallelization has on your particular machine. Then optimizing the best sequential program might not help you that much. It might actually be more worthwhile for you to keep some of that parallelization in there and see how that works on a single core versus a whole bunch of cores. That's not a terrible way to present it. The bigger point, I think, though, of this slide is you have to be clear, or when reading a paper or analyzing the results, right? The authors hopefully better be clear. You better understand what they're talking about so that you can take that speed up with that approach in mind. Because all of these are going to change the efficiency and the speed up numbers, sometimes maybe just out of carelessness or negligence, sometimes maybe intentionally to try and puff them up, right? It would not certainly be unheard of for people to try and do stuff like that. And so, yeah, this is the slide I was kind of thinking of a few moments ago. Ways to fool the masses when talking about parallelizing programs. This is an old list, as you can tell by some of the things that are on this list, but some of them still very much relevant today. So, comparing 32-bit results to 64-bit results, obviously not a fair comparison. That's not apples to apples at all. Inter-kernel results instead of the whole application. So basically, yeah. Assembly code. People don't write assembly code anymore. Actually, I love writing assembly code, but again, that puts me in the minority. I do it kind of for fun as a hobby in my spare time, but people aren't writing assembly code anymore, so that one's very much out of date. It's not an apples to apples comparison. Scaling the problem size with the number of cores, but not telling people that you're doing that. That is a big no-no. We're actually going to talk about that in a few more slides from now. There are valid applications for doing that, valid reasons for scaling the problem size with the number of cores. It's not a bad thing to do, but you got to tell people you're doing that because that has a huge effect on how you're going to interpret those numbers. Quoting performance results that have been linearly projected. So what that means is running it on a sequential and then just projecting what you think the speed up would be using some sort of linear fit or a regression model or something like that. Now that one, again, could have its uses, but if you're presenting that as these are the actual measured results running on that many cores, that is a problem. And people have done that. If you're going to do that, tell people that this is a projection. Maybe I don't have access to a machine to run, on that many cores, so I decided to use a linear projection instead. Perfectly okay to do, but you have to tell people that's what you're doing. Comparing scalar, oh yeah, there's a mention of Cray computers, just to kind of date this list even more. I don't think they make those anymore. Comparing old code on an obsolete system, coding performance of indirect measures. We use Speedup for a reason, although there's multiple forms of Speedup, as we're about to see. Using inefficient algorithms to get high flop rates. So cramming extra floating point instructions in there to make it seem like it's cranking out more floating point instructions than it actually needs to, inflating your numbers that way. Measuring parallel times on a system that is not doing anything else, but sequential times on a system that is trying to do 10 things at once. That's not a fair comparison. And then showing lots of nice pictures and graphs, but never actually telling me what the numbers are. All of these things are on the list because people have done these things before, right? These are also good things to avoid on your own reports, although some of them aren't relevant to your own reports. Some of them are. Not a super important list, but just wanted to think about examples of things that people have tried to pull off in the past. All right, let's talk about limitations to Speedup. This was actually a hot debate back in the day. You can see Amdahl's law way back in 1967. So Amdahl was a bit of a skeptic regarding parallel programs back in the 60s. He was looking at this and thinking about how to analyze the speedup of a parallel program. So he said, all right, we're going to take our program and we're going to partition it, where the blue represents the sequential part of our program. I cannot parallelize that part, right? It has to happen on one core. There's almost always going to be some part of our code that is not parallelizable. So that's represented by the blue part. The green part is the section that is parallelizable. So that's the part that I expect to improve once I start running it on more and more cores. And so we have our program in fractional parts. P is the parallelizable part, and 1 minus P then is going to be our sequential part. And so our speedup can be represented, if I run this on a whole bunch of cores, you can see that the P section shrinks by the number of cores, that we're expecting to use, or the speedup, in other words. So as the speedup goes up, that means that this section shrinks and shrinks and shrinks and shrinks. Everybody with me so far? So what's the issue with this? This all seems well and good. What's the problem? Why is Amdahl so skeptical about this? Well, if you think about this, and I know there's a whole bunch of math here, but try and boil this down in the least complicated way as possible. If t is our total execution time, we're going to write that as the sequential part multiplied by the time, and then our parallel part multiplied by the time. So our parallel execution time then becomes the sequential part remains unchanged. We now just have this S factor, the speedup factor, on the parallel section of our execution time. And then we can kind of reformulate our speedup as this over this, right? This equation over this equation. There's a bunch of algebra in here that simplifies out and leaves us with this equation. 1 over the sequential section plus the parallelized section. And the really interesting part is not the formula, not all of this algebra that we've done, but the implications of it. So our speedup, the maximum speedup that we can obtain is shown over here on the right, based on the essentially the sequential portion of our program is going to limit how much speed up we can get. Because I can shrink that parallel portion down, shrink it down, shrink it down, shrink it down, but the total execution time is never going to get less than the sequential portion because I can't shrink that section down. That cannot be minimized in any way. So here is a plot. Notice on the x-axis, we're actually going logarithmic. And the y-axis is linear, showing us as we increase the number of processors, what is the expected speedup that we get? And the thing to notice here is that they all eventually plateau. They all eventually flatten out. So if the blue line, which is the lowest one here, says that 50% of our program is parallelizable, the other 50% is sequential. I can't shrink that anymore. So the maximum speedup that I can ever hope to get is 2. And that kind of makes sense, right? If I can shrink the parallel part down, all the way down, all the way down, and I'm just left with the half that is sequential, that's going to get me a speedup of 2. The execution time is t, and I've cut it in half, so that's a speedup of 2. But that's the best that I'm ever going to get if my program is 50% sequential. Now, we can analyze this for other sequential executions as well, but notice that even if 95% of our program is parallelizable, meaning that only 5% of it is sequential, the maximum speedup that I'm ever going to get is 20. The absolute maximum speedup that I am ever going to get is 20. It's going to cap out. There's a limit. Amdahl's law says that there is an absolute limit to how much speedup you can get out of a program. And so Amdahl's argument was, hey, parallelization seems great, but if you're trying to get better speedup numbers, I think you're probably better off designing better chips that can run the operations faster. And back in the 60s, he was right, actually. Chips were in their infancy, right? Transistors hadn't been around very long. They were still giants compared to the transistors that we're able to manufacture today. Chip design was in its infancy. All the bells and whistles that you find on a modern CPU, like pipelining and branch prediction and stuff, were, if they existed, were rudimentary. They had not been well developed. So Amdahl in the 60s was correct. If going for maximum speedup is your goal, if improving the performance of your program is your goal, you're better off making better chips than trying to improve the performance of your program via parallelization. That law, though, really started to waver once the development of chips started to reach more of a critical mass. When that happened is up for some debate. A lot of people point to when multi-cores started to become more prevalent, which would have been in the 2000s, 2010s at the absolute latest. Some people point even earlier than that to the 90s when we were kind of on the cusp. Like Pentium 4 was kind of a landmark chip back in the day. I don't know if any of you are old enough to remember that. I definitely had one of those in my PC back in the day. I was just a kid, so it was my dad's PC, let's be real. But still, I remember the Pentium 4 commercials. It was a big deal. But regardless of when that transition actually happened, at this point in time, even the chips that are using on the supercomputers are maybe slightly fancier versions of the chips that we're using on our own machines. Back in Amdahl's time, that wasn't true. The chips they were using on the supercomputers in the 60s and the 70s were usually custom-built chips for specific purposes. So chip design needed some time to catch up. But so Amdahl, I think, had some good insight here, but there was another guy, Gustafson, who didn't agree with Amdahl, and they got in some heated fights. You can actually read some of their correspondence. I wouldn't say that it is nasty, but it's definitely a little snarky at times. They were not fans of each other. They did not agree on this particular topic, and they were not afraid to state how much they disagreed with each other on this particular topic. Gustafson came along and said, well, okay, I'm going to view parallelism not just really in terms of time, but in terms of the amount of work that is done. the more cores that I have, the more work I can do in the same amount of time. That was Gustafson's proposition. So if we take Gustafson's law into case, what that really means is that we're scaling the problem size up with the number of cores. The problem size is not staying the same. As we have more cores, we're able to do more computation, so I'm going to make my problem size bigger and get more work done in the same amount of time. So if we view this model from Gustafson's perspective, that changes the math a little bit. Here's our fractions. These are actually the same as before, but then the speed up, you can see this green section gets bigger. The amount of time is the same, but the amount of work that is being done is bigger because I'm able to get more work done in the same amount of time. So if W is the total amount of work, we can define that as the amount of work done in the sequential part plus the amount of work done in the parallel part. That's for the sequential algorithm. For the parallel algorithm, we then have that factor of S, that's our speed up factor, right, coming into play. And that, again, with some algebra, we compute speed up as our parallel over the, we're actually looking at this in a throughput model now because the parallel's on the top. So we're talking about speed up in terms of work done, not time saved. So this is a throughput computation of speed up with the parallel term on the top, the sequential term on the bottom, do some fancy algebra, and you get your speed up computed as 1 minus the number of cores plus speed up times the number of cores. And so if we look then at what the bounds of speed up are, using Gustafson's law, using Gustafson's view of the world, let's take a look at this graph. Notice on our x-axis, this is still number of cores down here, but it doesn't even go up nearly as high as the last one did. The last one went up to like 65,000 cores. This one only goes up to 120. And that's all we really need to actually show the difference between these two models. Again, if we look at, we started with the 50% model, which actually would be like right about here. And in using Amdahl's law, with a parallel speed up of, with a parallel section that was only 50% of our code, the max speed up we could get was 2, right? Using Amdahl's law. Using Gustafson's law, you can see that, okay, it doesn't stop at 2, it just keeps going. It never plateaus, it never flattens out. It says, you know, the speed up is boundless. If I have a bigger parallel section, then the speed up grows faster, right? And if I have a smaller parallel section, the speed up grows slower, as we see down here, but it never tops out. It never reaches that plateau like it does under Amdahl's law. And so really, who was right, who was wrong? Well, they both were. They both were right, and they both were wrong. If my problem size is fixed, right? If I'm solving a problem and having more cores means that I'm just solving that same problem, Amdahl's law applies, right? Amdahl's law is very valid. If my problem size is scalable, if I can grow my problem as the number of cores grows, which, by the way, is very common, especially for LLMs. They want to make their matrices as big as they possibly can. So the more cores they have, the bigger the matrices they have, the bigger matrix multiplies they're trying to perform. So making those AI models is a perfect application of Gustafson's law. Then our speed up is boundless. How many cores can you throw at it? You're going to get a lot more work done. You're going to get a lot more stuff done the more cores that you have. So this is a much more optimistic view of parallelization than Amdahl's law. Neither of them is wrong. They both are kind of telling a different story of different problems. Back in the 60s, they didn't agree with each other, but these days, I think both of them are respected for providing these laws under these different contexts. But yeah, the big difference there is speed up versus scaled speed up. So knowing how or even whether we can scale the problem matters. And what's difficult about that is that the problem size is not included in our computation speed up anywhere. And none of the In none of the computations of speedup that we've shown have we actually included the problem size as a term of that equation, right? With scaled speedup, we scaled the problem size with the size of the machine, and so our speedup actually taking the problem size into account comes a little bit different to compute. There is an implication that our problem is O to the n. Let's be honest, we're not trying to run any quadratic or exponential algorithms on these computers anyway. That is not a good use of our time. So that's not a terrible assumption to make. And the big takeaway, I think, from all of this, as it relates to you all, is, as I mentioned earlier, being able to talk about these things on your homework assignments when the appropriate time comes, which will be the next homework assignment, homework 2. This will be relevant. The first one is not parallelized at all, so not really relevant for the one that you're currently working on. I was talking to a few people during break. This is one that's kind of a training wheels assignment in a way. Actually, I was talking about something that I think would be relevant to the whole class, so I kind of want to repeat something that I mentioned. Is it Drew? Yeah, to Drew during the break. This is a common thing that happens when you're doing the data collection piece, I know I went through the whole spiel about error bars and histograms and stuff, right? What if all the data you collect is really tight? What if it's all like super tight together, and you go and you plot it, and the error bars are just like on top of each other almost? In that particular case, it's perfectly okay to tell me that. It's perfectly okay to say, hey, I did 20 runs of this, but they were all squished together. The error bars are too small to be seen on the plot. I promise you I could compute that and show it to you, but they're all squished together. In that case, it is perfectly acceptable to not put the error bars on there and just state that. State that in the text, in the results portion of your report, using the median probably as the point that you're going to plot. And then, should it be relevant for you to do so, zoom in on one of them and make me a histogram for one of them, right? To show me the distribution at that particular point in time. Especially if there's a particular point of interest, right? If one of those points is particularly interesting, or if a couple of them are particularly interesting and worth talking about in more detail, then zoom in and give me a histogram for one of them, or two of them, depending on what you're the point you're trying to make, but you don't necessarily have to do it for all of them. So that was a good conversation that I had. I just wanted to make sure that the whole class is aware of that as well. Otherwise, I know we still have time left, but I'm done today, and I don't have anything else on my agenda to talk to you about. So yeah, I'll happily stick around if you have questions, if you want to work on the homework assignment, if you have questions on the homework assignment, I'm here. I'm happy to stick around and chat, but if we're done. So thanks for coming, everybody. Wednesday, bring your computer if you remember to, because a lot more hands-on activities for us to do on Wednesday than there are today. Thanks, everyone.